Next chapter, uniform circular motion. Now, the motion of an object along a curved path is called curvilinear or circular motion. Uniform circular motion, therefore, is the movement of an object along a curved path at uniform or constant velocity. In other words, its velocity does not change with time. But although its velocity does not change, its direction is continuously changing. At all instances, the object is moving tangent to the circle. And so, its velocity does not change in magnitude, but changes in direction. And because the direction of the velocity vector is the same as the direction of the object's motion, the velocity vector is directed tangent to the circle as well. Angular displacement. Now, angular displacement is defined as the angle in radians through which a point or a line has been rotated about a specific axis. It is the angle made by a body moving in a circular path. Consider a particle moving along the circular path from A to B. The arc AB represents the distance s, while the angle theta subtended by the arc AB is the angular displacement. In circular motion, angles are measured in radians. And this is the ratio of arc length to radius of the circle. And so theta in radians is equal to arc length AB over radius OA, that is equal to S over R. When S is equal to R, then theta is equal to 1 radian. By definition, a radian is an angle subtended at the center of a circle by an arc of length equal to the radius of the circle. If the object made a complete revolution, the arc length will be equal to the circumference of the circle. Calculating, theta is equal to circumference over radius. The circumference of a circle is given by 2 pi r, and therefore theta in radians is equal to 2 pi r over r. Cancelling r out, we get theta in radians is equal to 2 pi. Remembering that a complete revolution is equal to 360 degrees, then 2 pi radians is equal to 360 degrees. Dividing both sides by 2 pi, it means 1 radian is equal to 57.3 degrees. And you can always use this relation to interconvert between radians and degrees. Next, angular velocity. Angular velocity is simply the rate of change of angular displacement with time. It is represented by the Greek letter omega. Angular velocity is equal to change in angular displacement over change in time. Omega is equal to delta theta over delta t. The units for angular velocity is radians per second. Now let's bring back the expression for angular displacement. Theta is equal to s over r. Dividing both sides by t, we shall have theta over t is equal to s over rt. Using small changes, we shall have delta theta over delta t is equal to delta s over r delta t. But delta theta over delta t is equal to omega, or the angular velocity. And therefore, if we substitute here, we shall have angular velocity, or omega, is equal to delta s over r delta t. Again, recall in linear motion that delta s over delta t is equal to v, where v is the linear velocity. Substituting this in equation 2, we shall have angular velocity is equal to v over r. Rearranging that, we shall have v is equal to r omega. And therefore, An object in a circular motion has both linear velocity given in meters per second and angular velocity given in radians per second. The linear velocity at any given point, or the instantaneous velocity, is tangent to the circular path. If the string holding the object in the circular path was to break, the body will proceed with this linear velocity. Let's take two examples. Example 1. A turntable makes 60 revolutions per minute. Find the angular velocity in radians per second. A revolution is one complete turn, or 360 degrees, which is equal to 2 pi radians. How about 60 revolutions? That will be 60 times 2 pi, which gives us 376.8 radians. We know that angular velocity is equal to theta over t. That is 376.8 over 60 seconds, that is 1 minute, and that gives us 6.28 radians per second. Example 2. A body moving in a circular path makes 75 revolutions per minute. If the radius of the circular path is 50 centimeters, calculate its linear velocity. 1 revolution is equal to 2 pi radians, and therefore 75 revolutions will be equal to 75 times 2 pi, which is equal to 471 radians. Omega, or the angular velocity, is equal to 471 over 60, that is 1 minute. That gives us 7.85 radians per second. And finally, linear velocity v is equal to 7.85 times 50 centimeters is equivalent to 0.5 meters. That gives us 3.93 meters per second. Next is period. Now, when a body moves in a circular path at uniform velocity, the time it takes to complete 1 revolution is called period t. It is measured in seconds. And so period t is equal to circumference over the velocity, which is equal to 2 pi r over v. But v is equal to omega r, and therefore t is equal to 2 pi r over omega r. The radius cancel out, and we shall have t is equal to 2 pi over omega. Let us play around with these expressions. We can rearrange them to have omega is equal to 2 pi over t. Since t is equal to 1 over f, then omega is equal to 2 pi f, where f is the frequency of rotation. We can also play around with this expression, omega is equal to 2 pi over t. Recalling that omega is equal to v over r, then v over r is equal to 2 pi over t, and therefore if we rearrange, t will be equal to 2 pi r over v. And so for this equation in example 1, we can calculate the period for the turntable. Period t is equal to 2 pi over omega, and we found that omega is equal to 6.28 radians per second. If we substitute, period t is equal to 2 times 3.14 over 6.28, giving us 1 second. Next, we look at centripetal acceleration and force. Now, we said that for a body moving in a uniform circular motion, the magnitude of its velocity remains constant, but its direction changes. And because the direction of velocity is changing, then the body is said to undergo acceleration. If you recall Newton's first law of motion, that is the law of inertia, objects in motion stay in motion with the same speed and same direction unless acted upon by an external force. Now in our case, the velocity is changing in direction, and that means there is a force acting on the body. Towards what direction does the force act? If you hold a string tied to a stone on one end and you swing it in a circular motion, you will feel that the stone tries to pull the string away, and you have to apply some force to keep the stone in the circular path. The force that the stone exerts on the string, trying to pull itself away from the center of the circle, is called centrifugal force. The counter force, which you have to apply to keep the stone in the circular path, is called centripetal force. Therefore, when a body moves in a circular path, the force which acts towards the center is called centripetal force. For this case, centripetal force is equal to the tension in the string. The centripetal force for motion of a planet around the sun is the gravitational force on the planet due to the sun. This is the force that keeps the body in the circular path and causes change in the direction of velocity and hence acceleration. The acceleration due to centripetal force is called centripetal acceleration. This acceleration is directed towards the center as well. Centripetal acceleration is given by v squared over r. Its units are meters per second squared. How about the centripetal force? From Newton's second law of motion, force is equal to mass times acceleration, or ma. And we already have centripetal acceleration, and therefore centripetal force is equal to mv squared over r. Its units are newtons. From this expression, we can see that centripetal force is affected by three factors: mass of the body, velocity of the body, and the radius of the curved path. When the mass increases, the centripetal force increases. When velocity increases, the centripetal force increases as well. But when the radius increases, the centripetal force decreases. Let's take an example. A body of mass 400 grams is tied to a string and swung in a horizontal circular path of radius 2 meters with a speed of 3.5 meters per second. Calculate the centripetal acceleration and tension in the string. So, centripetal acceleration is given by v squared over r, which is equal to 3.5 squared over 2. That gives us 6.125 meters per second squared. The tension in the string is equal to the centripetal force, that is equal to mv squared over r. That is equal to 0.4 kilograms times 3.5 squared over 2, and that gives us 2.45 newtons. Next, let's look at some few examples of circular motion. We start with critical speed and banked tracks. Now, when a car takes a turn, each curved section can be estimated to be an arc of a circle with a certain radius. A centripetal force must act towards the center of the circle to enable the vehicle move along it. This centripetal force is provided by the static friction between the road and the car tires. The normal force N balances the weight of the car, mg. If the coefficient of static friction is mu, the maximum friction force which can act towards the center of the arc is mu mg. While making a turn, if the velocity of the car is v and the radius of the arc is r, the centripetal force acting on it will be equal to mv squared over r. For the car to make a safe turn, the required centripetal force should be less or equal to the static friction, which implies that the velocity of the car should be such that it satisfies the relation mv squared over r is less or equal to mu mg. Cancelling out the m's, v squared is less or equal to mu rg, and v is less or equal to the square root of mu rg. This is called the critical speed. If the car moves at a speed greater than this critical speed, it skids away from the center. Now, we cannot always rely on friction because it depends on external factors such as rain, which significantly decreases the value of static friction. To avoid skidding of vehicles around turns, the outer edge of the road is raised up, which is called banking. Suppose the surface of the road at a turn makes an angle theta with the horizontal axis. This results in a horizontal component of the normal force n sin theta acting towards the center and providing the necessary centripetal force at the turn. Friction is not taken into consideration here, and therefore n sin theta is equal to mv squared over r. The vertical component of the force balances the weight of the vehicle. So n cos theta is equal to mg. From these equations, n sin theta divided by n cos theta will be equal to mv squared over r divided by mg. And that is equal to mv squared over mrg. The m's cancel out here and the n's cancel out on the other side. We remain with sin theta over cos theta is equal to v squared over rg. But sin theta over cos theta is equal to tan theta, and therefore tan theta is equal to v squared over rg, meaning v squared is equal to rg tan theta, and v is equal to the square root of rg tan theta. This equation gives the speed in which, in the absence of friction, for a given angular inclination and radius of curvature would ensure the car does not skid away. The critical speed does not depend on the mass of the object. And so for a horizontal track, critical speed Vc is equal to the square root of mu rg. And for a banked road, the critical speed Vc is equal to the square root of rg tan theta. The turning of aircrafts in air is made possible by the gradual lowering of the wing on one side. This makes use of some component of the lift force to provide the necessary centripetal force to enable the aircraft move in a circular path. Next, we look at vertical circular motion. Now, consider a ball of mass m tied to a string and swung with uniform speed in a vertical circle of radius r. The forces acting on the ball at any instant are its weight mg, which acts vertically downwards, and the tension T, which is always directed towards the center of the circle. The tension in the string changes in magnitude at different positions of the ball. When the ball is at point A, the tension TA and the weight mg provide the centripetal force. Therefore, mv squared over r, the centripetal force, is equal to Ta plus mg. This means that Ta is equal to mv squared over r minus mg. When the ball is at B, which is the lowest point of the path, it is acted upon by the tensional force Tb and its weight mg. The centripetal force, therefore, is provided by the resultant force Tb minus mg. Rearranging, Tb is equal to mv squared over r plus mg. From these equations, it is evident that Tb is greater than Ta. The tension in the string is therefore maximum when the object is at its lowest point and the string is most likely to snap at this position. Also, from the above, it is clear that the tension is minimum when the object is at its highest point of the circle. It is at this position that a certain minimum speed must be maintained in order to keep the string taut. For minimum velocity, Ta is equal to 0. And therefore, mv squared over r minimum minus mg is equal to 0. And therefore, v minimum is equal to the square root of rg. At position C and D, the weight mg is perpendicular to the tensional force and hence do not contribute to the provision of centripetal force. Therefore, Tc is equal to Td and is equal to mv squared over r. Now, let's talk about some applications of the vertical circular motion. Now, consider a person swinging a bucket with water at constant speed in a vertical circle. How can the water stay in the bucket? Let's consider the water when the bucket is in its topmost position. At this instance, the water has a horizontal velocity v. The gravitational pull would cause the water to continue along a parabolic arc. The bucket, however, follows a circular path. Relative to the circular path of the bucket, the parabolic path would have taken water to the top, breaking the base of the bucket. To avoid this, the bucket exerts a downward normal contact force on the water, just enough to push the water into following the same circular path as the bucket. When moving past the top in circular motion, the normal force N of the bucket based on water provides the centripetal force mv squared over r, which must be greater than mg, that is the gravitational pull, if the water is to stay in the bucket. And therefore, mv squared over r must be greater than mg. Cancelling out the m's, we have v squared over r is greater than g. Therefore, v squared is greater than rg, and v is greater than the square root of rg. The water falls out of the bucket only if it falls faster than the bucket. As long as the bucket is swung at a high enough speed, this will not happen. Next, Lambert tracks. Now, when you're in a car that is going over a hill or down a valley bottom, people know that sometimes they get a funny feeling in their stomach and you actually feel lighter or heavier for a moment. There are two forces acting on the vehicle or any other body for that matter. The weight mg of the car, which is constant, and the recusation force R, which varies and acts in a similar way as tension in a string. We also call it the support force. Now, consider a car of mass m traveling at a speed v over the top of a hill with radius of curvature r. At the hilltop, R, or the recusant force, is in the opposite direction to the car's weight. Because the path is curved, the resultant force, which provides the centripetal force, must be the difference between these two forces. So mv squared over r is equal to mg minus r. At a certain speed, the car would lose contact with the road, and this happens when r becomes 0. If r is equal to 0, then mg is equal to mv squared over r. Cancelling out the m's, g is equal to v squared over r, and rearranging, v is equal to the square root of rg. This is the maximum speed that the car must travel to remain in contact with the road. And from this, we see that we can find out that maximum speed by simply getting the radius of curvature. Again, this maximum speed has nothing to do with the mass of the car, which is surprising actually. We take two examples as we finish. First one, a vehicle of mass 1,200 kilograms passes over a bridge with a radius of curvature of 15 meters at a speed of 10 meters per second. Calculate 1. The centripetal acceleration of the vehicle on the bridge. 2. The support force when at the top. And 3. Maximum speed without losing contact with the road. 1. Centripetal acceleration is given by v squared over r, that is 10 squared over 15, and that is equal to 6.67 meters per second squared. Secondly, the centripetal force mv squared over r is equal to mg minus r, and therefore r is equal to mg minus mv squared over r. 1,200 times 10 minus 1,200 times 10 squared over 15 by 15.1 by 1580. That gives us 12,000 minus 8,000, and that is equal to 4,000 newtons. Finally, maximum speed v is equal to the square root of rg, that is the square root of 15 times 10, and that is equal to 12.25 meters per second. At the valley bottom, R and mg act in the same direction, so the resultant force which provides the centripetal force mv squared over r is equal to mg plus r. The final example. The critical speed of a 750 kilograms vehicle at a roundabout of radius 20 meters is 9 meters per second. Calculate A. The centripetal acceleration, B. The centripetal force on the vehicle, and C. The limiting force of friction if the car skids at 16 meters per second. A. The centripetal acceleration is equal to v squared over r, and that is 9 squared over 20, which is equal to 4.05 meters per second squared. B. The centripetal force is equal to mv squared over r, that is equal to 750 times 9 squared over 20, which gives us 3,037.5 newtons. And finally C. The limiting friction is equal to the centripetal force, and so F naught is equal to mv naught squared over r, that is 750 times 16 squared over 20, giving us 9,600 newtons.